to the right. And so you can see that the Schwartz perturbations have the largest perturbations at large scales initially, whereas random CV, for instance, they're a tuned perturbation to a particular scale of around 400 kilometers or so. And so you don't see any energy at small scales. Whereas our Ensemble common filter perturbations, which is the expensive ones that we make ourselves, those have a lot of energy at small scales, but they tend to tail off at large scales. So if we go 12 hours into the forecast, it turns out that those random perturbations are the ones that are growing the fastest. And so there's this kind of big flop that maybe says, well, there's something interesting there. Are those random perturbations actually good error growth? And then the answer to that's kind of mixed. So if we look at skill based on perturbations, so there's kind of a lot going on, a lot of lines in these plots on the right. So we'll try to break this down a little bit. So first, just pay attention to the solid lines versus the dashed lines. So higher values in these metrics, this fraction skill score for precipitation at different thresholds, higher values indicate greater skill. So the dashed lines, as you can see, are quite a bit lower than the solid lines. And that's basically a representation of the skill of the mean analysis. And so if the mean analysis is poor, then the forecasts are going to be poor. And so that's the first, most important thing to fix. Perturbations are secondary. That said, among perturbations, you can see that the red line is lower than the other two. And so what that basically says is that the random perturbations actually produce less skillful forecasts. So while it may be growing a lot in terms of perturbations, those perturbations aren't growing in a skillful way. And we can see that also if we look, for instance, in reliability diagrams. So you want to be along the diagonal from lower left to upper right for a skillful forecast system. And what you can notice is that the least reliable forecasts are the ones that are from our Ensemble Kelvin filter. And so those perturbations are just not growing in the ways that we want. But just by looking at these types of metrics, it's actually really hard to try to understand the ways in which these perturbations are growing and what's working and what's not. And so we've been trying to think about different ways of looking at this, and this spurred our interest in using a wavelet analysis technique. And this idea of looking at central scales to try to define the relationship between our errors in the forecast and where the spread is occurring in the forecast. So our thinking is that what you really want is consistency between where the forecast has errors and regions where the forecast is growing spread, so that those two are kind of co-located in space. And so this technique basically takes a look at the field and then tries to look at the how much variability there is in the spatial sense of the field. What you'd like to see is a good consistency between places where you have error growth and places where the ensemble, or where you have it, consistency between where the forecast has errors and where your model system agrees that that forecast was uncertain. That's probably a better way to put it. So this is based on a method by Bouchau et al. And so using that method, we can start to kind of break apart the spread skill consistency and then look at the skill of that. And so in this particular case, we're looking at joint probability diagrams for the different initial perturbation methods. And so let's see, seems that hang on, seems I lost my labels on these, but so the one on the left is for random perturbations. The one in the middle is for SREF, short range ensemble forecast system perturbations. And then the one on the right, far right, is from the ensemble common filtered. And so you could clearly see that there's a lot more variability in the scales of the perturbations from the short range ensemble forecast system, whereas they're really flat in both the DART and the random perturbations. But the random perturbations, again, it has that sort of favored tuned spatial scale of 400 kilometers, and that doesn't really show a lot of good correlation. You'd like to see these joint probabilities basically moving along the diagonal. And we could try looking at this in different fields. So for instance, these are different surface fields and looking at that Pearson correlation coefficient. And you get a pretty mixed message looking at things this way as well in terms of, what kind of perturbation type is leading to the most consistent matching between the spread and errors. And as you can see by these lines, that that correlation is kind of bouncing up and down. It's definitely got some diurnal cycle dependency. During the day, there's a lot more variability than during the evening and overnight hours, but it's all kind of a jumbled mix. So another way we could potentially look at this would be to say, look at Molar diagrams. And so in this case, this is Molar diagrams of skill, spread, and consistency ratio. And so within each panel, time is increasing from the bottom to the top. And so if you just, for instance, focus on the very upper left panel, so that's the, oops, wrong button. This is the central scale for mean squared error. And what you'll notice that there's quite a bit of diurnal cycle variability. And so for instance, there's a peak to larger scales at roughly 24 hours, and then it fades back off again and goes back to smaller scales in terms of mean squared error. If you go to the second row, that's the spread. And what you can immediately note is that that diurnal variability is not being well represented within the Ensemble system. So all of the ensembles are basically showing very consistent diurnal variability that doesn't match the errors that are showing up in the forecasts. And so that's definitely one thing that's worth noting. And then if you move from left to right along that middle row with spread, you can also see that in terms of increasing time from the bottom to the top, that the first two types of perturbations with random and Schreff perturbations aren't really growing much over time as the forecast integrates, whereas the flow-dependent ensemble common filter perturbations do seem to show a fairly consistent growth rate with time. So there's definitely some interesting differences between these, but we're still trying to kind of make sense of this in this study. But we feel like this tool is definitely giving us more insight than where we had before. All right, so another thing that we could potentially do, we've talked about, what are we really hoping to do is both, get error growth in the right place, but we're also trying to improve the mean skill of the background. Because if we put a more skillful background into our analysis system, then we're going to get a better analysis and a subsequent better forecast. So one of the ways that we can go about doing that is to potentially improve the representation of convection in our background analysis. And so historically, the work that we've done here at NCAR, we've used 15-kilometer analysis. And so we're having to leave a convection cumulus parameterization on for our cycled analysis system, and then we make 3-kilometer explicit forecasts where we do a downscaling from the 15-kilometer analysis. And so what we wanted to explore was, what if we just went straight to 3 kilometers for our cycled analysis system? So now we don't have to introduce those downscaling errors when we initialize the forecast, and hopefully by explicitly representing the background convection, we'll be able to more effectively use the available observations. And so that's what we did, and we used basically full CONUS 80-member 3-kilometer analysis with I forgot where I was going to go with that. So, all right, let's just move on. Sorry, I'm going kind of fast here because I realize I have too many slides, but I'm going to try to get them all in. All right, so smoothing. One of the things that we kind of recognize is that when we run the regional analysis, and as we saw in those previous slides, the continuously cycled analysis, the forecast skill was kind of drifting off with time. And so we're trying to basically move that mean analysis skill back up again. And so there's a variety of different ways that one could probably achieve that, but one of the ways that we found particularly intriguing is to basically blend from large-scale global analyses. So in this case, we can go back to the GEFS, or Global Ensemble Forecast System, and we can basically borrow the large-scale analysis that's quite skillful from that system and push it back into our regional system to account for all the ways that regional systems tend to no longer maintain skill after a long period of cycling. And so we're using a fairly large scale for this smoothing and blending, and we'll just give it a try and see how this goes. So here's a skill based on these different types of methods. So we're going to initially start off with, again, fraction skill score. So in this case, where, again, higher values are better, indicate more skill, and we're going from lower rain rates in the upper left to very intense rain rates in the lower right. And so if we look at the forecast from just borrowing from another Ensemble system and then downscaling, we can start from the GEFs. And what you see is that those forecasts are not very skillful during about the first 12 to 18 hours, but then they're pretty comparable. Whereas by the time we get out beyond 24 hours, those forecasts are now quite skillful relative to the others. Meanwhile, let's make our own analyses, but we use them with 15-kilometer background. So it's parameterized convection, and we have to do a downscaling into our forecast. And those are shown by the blue lines. And you can see that those are definitely better than going out and grabbing the GEFs, but they also tend to degrade with time, particularly as we get out beyond 24 hours. The forecast skill of those tends to kind of fall off. What if we go to a 3-kilometer background? And so that's the red line. And so you can see that the 3-kilometer background does add value, particularly at some of the more intense rain rates, which is a great thing to see for convective precipitation skill. And that value lasts out to roughly 12 hours or so where we're able to add value. But then again, when we get out beyond 24 hours, that value tends to kind of tail off. So finally, let's consider that blending option we talked about before. So what if we bring back in some of that large scale analysis value, and let's put it on top of the 3-kilometer initial conditions and see if we can kind of get the best of both worlds, get that more skillful early prediction capability, but then improve perhaps some of the sort of back end at the longer range forecast by including more of the large scale analysis. And that's what's showed in the black lines. And as you can clearly see, that we do retain most of that value in the large scale or in the extended range. So beyond 24 hours, we're able to basically hold on to that large scale forecast skill. But we also are retaining that small scale perturbation value in the short term. And so this does, in our opinion at least, provide positive benefit. All right. So in practice, if you go out and you look at, what are people actually doing, the sort of best practice with regional systems, because of this issue of regional models basically fading away as you continuously cycle, most of them have gone to what's known as a partial cycling strategy. So if you're not familiar with the difference between continuous cycling and partial cycling, there's a little graphic provided for you, a cartoon. The basic idea is in continuous cycling, every analysis is basically a forecast from the previous high resolution analysis that you did, and then you just do another short forecast and make another analysis and so forth and so on. This is the way that all of our global systems are set up. But because our regional systems have a known tendency to kind of fade away and not perform as well if we continuously cycle them, we've tended to resort to partial cycling, which has been the sort of mode of operation, for instance, within the higher resolution rapid refresh, where they'll go out and occasionally replace the background analysis with global analyses to restore that large scale quality. And so we wanted to figure out whether this partial cycling could be replicated with a blending approach. And so you could look at different ways of doing partial cycling. How long should you do partial cycling, things of that nature. And so we didn't want to test everything, but we were able to kind of look at a couple of different ways of slicing and dicing this. So first off, we did experiments where we took partial cycling starting from 6 UTC, and then partial cycling starting from 12 UTC, and in both cases making forecasts from 0 UTC and comparing that to the continuously cycled system. And so there's one thing that you can notice by looking at these measures of bias and root mean squared error for aircraft zonal wind, shown in the panels at the bottom, is that the bias tends to grow pretty quickly. And so this is basically an indication of fast error growth in our modeling system. And those are things that partial cycling is basically not fixing. Meanwhile, we could also see that there's just a surprisingly little difference in all of these for this particular field of aircraft zonal wind. But if we instead look at, say, aircraft relative humidity, this is something that we don't get as many measurements of relative humidity. And so in this case, you can see that there's a little bit more variability shown here because we have lots of temperature measurements from aircraft, but not many measurements of moisture. They're not as many. And so there's more space there that we're not hammering out by our hourly cycling. So what does any of this mean? So let's look at forecast skill. So again, fraction, or in this case, we're doing area under the ROC curve, but the same basic idea, larger values are better. And so you can see, there's a bunch of little lines on here that and for some reason the legend's missing. All right, so the different partial cycling ones are shown in orange and green. So the orange was from 6 UTC, the green was from 12 UTC partial cycling, and then the purple was our continuous cycling. And so just like what we saw before, there's this drop off in the continuous cycling, particularly beyond 24 hours, where those are just less skillful. And then the gray curve shown on here is if we just go back and we get those GAPS initial conditions again. And so those just take a long time to spit up, but then they're quite skillful beyond 24 hours. And so black line again is our blending. And so the blending is, again, a way where we can kind of get the best of both worlds. And so it holds on to our value in the short-term forecast, and then it also brings us up to the equivalent value of partial cycling in the long-range forecast. But when you think of the workflow differences between doing a blending versus doing a partial cycling system, which is quite a monster to actually run in practice, it's a considerable workflow benefit to be able to just employ the blending. And so that would be our recommendation. So what are some other things we can do? So part of what we're trying to figure out is, maybe our forecasts are just as good as they're going to be, and we should just try to find ways to add value to what we already have. And so artificial intelligence is definitely providing a lot of hope for how to achieve this. And so in this particular example, this is some work that Ryan Sobash is leading. So we have initial storm surrogate probabilities, which are shown by numbers. So this is, for instance, taking updraft helicity or something along those lines, which is a representative of a supercell storm within a convection allowing model. And then we're converting that to say, where we have rotating storms, we expect to see severe weather later in the day. In this particular case, those storm surrogates are located with very small numbers over parts of Missouri and Illinois, and you can see that the circle storm reports are actually offset by quite a bit. Not a great forecast here. So what can we do by applying artificial intelligence? Well, it turns out that using a neural network approach, we can get much better consistency between where the storm reports occur and what our forecasts are providing in terms of probabilities. And this benefits basically from using storm environment information. And you may recall from the very beginning of our talk, our models do a pretty good job of forecasting storm environment. And so we can kind of take advantage of that again by going back to these neural networks, because they can learn how to interpret the information you have and add value to it by combining it with known characteristics such as storm environment and rebuilding what those probabilities could look like. And indeed, we end up adding quite a bit of skill to these forecasts. And so this is a brighter skill score. So again, higher values are better. You can see that the orange line is the neural network probabilistic forecasts. And those are quite a bit better than our storm surrogate probability forecasts alone. And so this is extremely promising. And it also ends up with more reliable forecasts. So again, you want to be along that perfect diagonal to show that your forecasts are reliable in nature. And the neural networks do a great job of improving the reliability of our forecasts. There's other work that Ryan's leading, which is super exciting. So for instance, he's trying to do object-based convective mode forecasts. And so this is just a kind of a pretty graphic that's showing for a given convective scene, the likelihood of a convection that's present, whether it be a supercell, a quasi-linear convective system, or a disorganized convective system. These are really exciting research opportunities, and I think there's a lot of opportunity to get more value out of the forecast that we already have. So I'm excited to see that this work is moving along well. All right, so I do want to make just a quick pitch for some of the work that we're looking forward to. So this is work that we hope to get going with support from the JTTI program, and we'll have some new collaborators with Alicia Bentley and Jeff Manikin from NOAA EMC. And what we're going to be trying to do is really looking at diagnosing forecast errors within the medium range weather forecast system. And so what's shown here is an example from a particular forecast using two different versions of the GFS, so version 15 and 16. And these are 500 hectopascal height patterns along with vorticity overlaying. And then you can see the sort of blue dash showing where a shortwave is moving through the system. And the analysis is shown on the far right. And then the two forecast systems, in this case, they are, I believe, 96-hour forecasts. They're remarkably progressive in this case. And so you can see, one, that they don't even have the tilt of the trough correct, but they're also just way too fast in terms of merging this trough. And in this case, this was for a fairly high impact severe weather event that occurred across parts of Texas. And so this was an event that you definitely didn't want to get wrong. And yet these forecasts were not super useful because of this sort of progressiveness. And the pattern that's been noted in the GFS for this progressive aspect is that it tends to have these forecast errors when there's an upper level load that's either reconnecting back in with the flow or is emerging from the main flow. And so that's a very situational dependent forecast error. And so it's going to really require us to think more of an object-based approach to how we look for errors in the forecast system. And so that is something that we're really excited about digging into further. And so we're very excited to work with our new partners on this project. All right. So in summary, there's a lot of different things that could be done to try to improve our forecast systems. A lot of these are really still just a work in progress, but I feel very excited about some of these contributions that we've been able to make so far. We're definitely noting the value of adding, for instance, higher resolution background analyses. That said, they do come at a substantial computational cost. But also this idea of blending is a way to maybe get some of that back in terms of simplifying the workflow, and seems to add a lot of value in longer range forecasts from higher resolution ensembles. So that's been exciting. And then reliability forecasts, this is just hard, but we are trying to find new ways to look at this problem. I think some of the central scale idea has been pretty enlightening, but there's definitely quite a bit more work to do to try to figure out how to get our ensemble systems to grow error in good ways instead of in bad ways. That's a tough challenge. So, and then looking ahead, we're definitely interested in this sort of idea of investigating conditional forecast errors. And so with that, I will stop.
Okay, thank you so much. If anyone has any questions, please type them in the questions or chat box, and we'll be able to read them. So far, I don't see any questions.
Stacy, I've seen a lot of questions in the question box. You cannot see it?
I cannot see any questions.
Oh, all right.
So I think I can see some of these. So looks like the first one's from Jeff Duda. Can I get more info on the Baumgart et al. Reference so I can read it? Jeff, if you just want to email me, I can help you find it. But I think it's in Monthly Weather Review from 2019. This one's from Cliff. If convection is the largest contributor to uncertainty in the earliest portion of the forecast, might convection permitting resolution in our models potentially result in a significant jump of predictability? Well, I think that was sort of what we were demonstrating by going to a 3-kilometer background analysis. So that's definitely a place where we're able to kind of improve some of our representation in our analysis system before we use the observations by going to a higher resolution. And so that may be part of where we get some of that benefit. But part of what we're actually hoping for is that we want to tap into that error growth because we're trying to get more skillful spread growth as well. And that's the part that really becomes tricky to kind of chase after, because again, you want to improve the error growth, so the randomness representation, to get the skillful predictions. Yet at the same time, you're trying to knock down the systematic errors, and the two are heavily conflated, and sometimes it's hard to tell what you're actually achieving. So it's sort of like we're putting water and lighter fluid on our barbecue at the same time. So it's a challenging balance. This one's from Jimmy. For the blended forecast system, have you compared that to a control run where the lateral boundary and initial conditions come from blended analyses? I would say we have not. Getting at how close are we to how close are we to a baseline given the observing system? And what does it say about the parent forecasts versus lateral boundary conditions and resulting error growth? This would be one that might be good to talk out. Kind of a bummer we can't just do that. So we are perturbing the lateral boundaries, and that I'm sure that's a source of error growth. There's a lot of studies that have shown that error growth kind of comes in from the lateral boundaries. And in some ways, actually, we're trying to promote that error growth because we perturb the lateral boundary conditions in our Ensemble systems to try to help grow that uncertainty. So in some ways, it's that sort of we're actively trying to grow random growth in error while trying to knock down systematic error. The amount of systematic error that comes from lateral boundaries, that's a tough one. There's different ways of thinking about it. So for one, when you think of global analyses, they get a lot of value, for instance, out of satellite observations of microwave temperature. A lot of that doesn't seem to provide the same benefit in regional analyses for reasons that have never been, at least to my knowledge, well explained. But there's also observations that are outside of our domain that we just can't include because it's a regional system and we can't represent the forward operators for those because it's outside the domain. So there's a lot of reasons to expect that our large scale analyses in our regional systems is just not as high a quality as our global systems. So that's where we feel like a lot of the value is coming back in by incorporating those large scale blended analyses. Okay, can I get a reference list from this presentation? Jeff, sure, email me and I will hook you up. That's Jeff Duda. We have another question from Jeff Beck. Can you briefly describe how you blend the large and small scale feature to create the final analysis? So I showed before there was basically a filter. In this case, it's at It's centered at 960 kilometers, but you basically just do a spectral breakdown of the perturbation field, and then you can just sort by wavelength and then apply weighting to blend them back together again. And so you just basically throw out the large scales from your regional analysis and replace them with the large scale analysis from the external system. And the smaller scale wavelengths are all 100% from the high resolution analysis. And then there's a weighting function that does blending in between. From Krishna, in your training for machine learning, what are the factors that you have included along with environmental conditions? So the reference for that is, I think Sobash et al. I forget if it's 2019 or 2020. He's a busy guy. He writes a lot of papers. If you email me, I can give you the exact reference. So we started off with, I think there was around 80 different predictors that were thrown in, but a lot of those are fairly similar and provided redundant information. And so through a variety of different approaches, trying to look at the relative importance of the different training fields, I think he was able to reduce that down to something closer to on the order of about a dozen different predictors that were most important. But there's a lot of it in there that, for instance, just relates to the location. So you can imagine that one of the things that pops out, because you're training on storm reports have a lot of connectivity to social information. So for instance, the highly populated cities, you're much more likely to get a storm report out of those than, say, a very intense storm that's in a region that's very lowly populated, very little infrastructure. Those tend not to get as many storm reports. So the threshold for what it takes to sort of trigger a probabilistic prediction of a storm report spatially varies quite a bit. So there's a lot of value that comes in from that. Okay, from Fred Carr, you wrote, improving model skill is a faster pathway to better initial conditions. Faster than doing what else? Did you study value of adding new PBL observing systems? Not in this work. So we have done some other projects that I'm involved in that are looking at adding different PBL observations. For instance, vertical profiling systems from mobile and fixed observations. I don't think it's quite as easy. I mean, I'll go back to that example that I gave, for instance, with partial cycling. And what you really saw in the bias was that even 6 hours into the forecast, there was substantial error growth. And so those are fast errors in bias in the modeling system that grow at very quick rates. And those are really the kind of errors that we're trying to tackle most aggressively, is those sort of fast physics errors. Trying to figure out where they come from and what the right way is to represent them is a real challenge, because there's just not a lot of quality observations that are at the temporal scale of helping us kind of chase those down. But that's definitely something that we're interested in trying to find ways to get at. And that's where assimilating PBL observations is a great way to, for instance, look at the misfit between our model predictions and those observations to try to track down those types of systematic errors. All right, well, there's a lot of questions here. I don't know that I'm gonna get all these in the time here. Someone jump in and cut me off if you guys have to end this. So from Alex, for the progressive aspect of the GFS for storm systems over CONUS, I've been noticing that problem for quite some time and observed that it was more pronounced during the spring. SPC forecasters inform me that this could be due to winter climatologies embedded in the GFS, faster moving storm systems affecting the propagation speed of these storm systems. So I would say that I don't really have an initial thought or opinion on that. I mean, this is I think it's an interesting problem, and that's why we wanted to look at it more closely. So I think I'm going to defer on that one until we've had a chance to look at it more closely. But there's some expectation that, or at least hope that it might be physics related within the system, but that stands to be seen. From David Bright, where the neural network and storm surrogate probability forecast comparisons you showed near the end of your presentation from an ensemble or one deterministic forecast. So in that case, they were from deterministic forecasts. So the training data set was from a set of roughly 500 3-kilometer resolution forecasts, where a portion of those, so I think up to around 300 or so of those were used for training, and then forecasts of storm reports were made from the remaining set from the same consistent group. So there was a lot of consistency between the forecast system used for training and the forecast system used for testing. And then the probability then comes from spatial neighborhood with smoothing. Evan Kalina, do we understand why continuous cycle regional systems tend to drift over time? I think we have our suspicions that it's related to the factors that I talked about a few minutes ago, but I would say those are suspicions and not proven. And then from Curtis, is there any vertical weighting dependence of this blending from the GEF's large-scale information? I do not believe that we're doing any kind of vertical variation in that weighting, but that would be a question to ask Craig to be sure. I don't remember off the top of my head. So sorry, I can't answer that one for you, Curtis. And I think that was the last of the questions that I can see.
Yes, I'm able to see the questions now, and that was the last one. Thank you so much, Glenn. I have a copy of all of the questions, and I will email them to you so that you can respond to them accordingly if you would like, Glenn. I will send them to you.
Sure,
Okay.
that'd be great.
Okay, good. Thank you, everybody, for attending this UFS webinar series, and we will see you again in 2 weeks. Have a good day. Thanks, Glenn. Thanks, Chandra.